OCR A A-Level Chemistry, Module 5, Part 2. So this is going from electrode potentials up to qualitative analysis. Everything else is in Part 1. Starting off with definitions, hopefully you know these already. So an oxidizing agent takes electrons from species, is itself reduced, and a reducing agent adds electrons to species and is itself oxidized. Now, just to demonstrate what I mean, in this example here, silver is reduced and so is the oxidizing agent, and copper is oxidized and so is the reducing agent. You can write reduction and oxidation half equations like this, where you just reference the ions and the electrons that go with them, and then you can turn it into a full equation. So as you can see here, our electrons aren't balanced. Our reduction has 2 and our oxidation has 3. So we're going to want to balance the electrons first. So we're going to times our reduction by 3 and our oxidation by 2. That gives us these two equations here. Now what we're going to do is add all the reactants together and add all the products together, which gives us something like this. And you're like, excuse me for using multiple lines, I ran out of space on my whiteboard. You can start cancelling things out. If you have something in the reactants and the products, then there's no change, so it doesn't need to be in the reaction. So first we're going to take out our 6 electrons. That leaves us with this reaction here, with our electrons gone. Now what we need to do is look at what these sides have in common. So we have OH minus ions on both sides of the equation, but we've got different numbers. So all we're going to do is minus the products from the reactants. So we're going to end up with 10 OH minus ions in the reactants. Now you can also use oxidation numbers to balance equations, especially difficult ones where an element is maybe in more than one product. So this one's very difficult to balance because oxygen is present in all 3 products. So all we're going to do is write out the oxidation states first. So now we need to make them equal. So we're going to times our reduced products and reactants by 6, which in this case is nitric acid and nitrous oxide. So you put a 6 in front of those 2. Then once you've done that, you just have to balance it like you would any other equation in chemistry. So now you need to know about redox titration, and it's the same as any other titration. You're going to put potassium manganate in your burette, and your thing in your conical flask will go colourless to pink. Now the problem is potassium manganate is very dark purple, so you need to read the meniscus from the top, but because it's titration, the reading is all about the difference, and so as long as you're consistent, it should be absolutely no problem. You can also use sodium thiosulfate, which you put in your burette and you use starch as an indicator, and it will go from a blue, blackish colour to a pale kind of straw coloured yellow. Now we need to learn about standard electrode potential, which is something's tendency to be reduced and gain electrons. Which leaves us with something called a standard half cell, which is hydrogen gas dissolved in hydrogen ions. There's a platinum electrode and there are standard conditions. So solutions are in 1 mole per decimeters cubed. You're looking at 298 Kelvin and 100 kilopascals. So hydrogen gas enters a tube that's got holes in it that keeps pressure at 100 kilopascals. And the platinum electrode reacts with the acid solution, and we call this a hydrogen electrode. This produces 0 volts. It's a half cell. It produces absolutely no electricity whatsoever. Or if you connect it to a copper electrode, then you end up with a current, except you have to add in a salt bridge for the ions to transfer across. Electrons flow from the hydrogen half cell to the copper electrode, and you can read the voltmeter in a practical to find out the electrode potential. Negative standard electrode potential means a larger tendency to lose electrons or oxidize, and this is normally metals. The more negative it gets, the more reactive it is. Positive electrode potentials have a larger tendency to gain electrons or reduce, and these tend to be non-metals, and the more positive the value, the more reactive it is. Find the electrode potential of a cell by doing the positive electrode minus the negative electrode, or the anode minus the cathode. Now you can have metal-metal cells, and that's a metal rod dipped in its metal anion solution, and it creates an equilibrium at the phase boundary. Now, convention states that you do the reduction as the forward reaction and the oxidation as the backwards reaction. Now, in a half cell by itself, or an isolated half cell, there is no electron transfer. However, in two half cells, it depends on each electrode releasing their electrons. Most negative electrode is oxidized, and the most positive electrode is reduced. And this makes sense because obviously opposites attract. So you can work out the overall equation with this principle. So in this C, silver has the highest electrode potential value and so has a greater tendency to be reduced. So because it is an oxidizing agent, it will react with the reducing agents on the right hand side of systems A and B. So the silver ion will react with the chromium or copper atoms. So now we need to compare A and B, and copper has the higher tendency to be reduced, and so the oxidizing agent would react with chromium. And the chromium ions won't react because there's no redox systems with less electrode potential. So, remembering our convention that reduction is left to right and oxidation is right to left, we can write out what happens. So, chromium reacts with both silver and copper reacts with silver. Now, as always with these things, there are limitations. The reaction rate's not indicated. Electrode potential cannot be standard. There can be, different concentrations. And then there's the problem with, other non-standard conditions, temperature, pressure, etc. Now, batteries work by having two electrodes with different electrode potentials, and there are three types: primary, secondary, and fuel cells. Primary cells are non-rechargeable and they're single use, but they do have a low current, which means they do have longer lives. Secondary cells are rechargeable, so the reaction is reversible, and we're thinking about things like lithium here, which is present in phones, laptops, any electronics you might own. Lithium is light and it has a really high energy density, but it can be unstable at high temperatures. As any of you will know, if you remember the Samsung S7s from a couple of years ago that started exploding and it was all over the news. And there's also been cases of lithium battery fires at recycling centres and scrapyards, places like that. Finally, fuel cells. They create energy from a reaction of fuel with oxygen. Fuel and oxygen go in, the product comes out, and the electrolyte stays in the cell. An example of this is hydrogen cells, which don't produce CO2, only H2O. And they either have an acid or an alkali electrolyte. OH is produced at the anode and H+ ions are formed at the cathode. Moving on from that, we have transition elements, which are in the D block, which I've mentioned many times is how you distinguish parts of the periodic table. Now for A level, you only need to know about period 4, which has the outermost subshell of 3D. But remember, you always fill 4s2 first. Filling 4s before 3D means that you have to empty it before 3D as well. Now, just to make things complicated, there are exceptions, namely copper and chromium, and they fill singly before they fill pairs because it is more stable. So you need to be able to define what a transition element is, and it's a D block element that forms at least one ion with a partially filled D orbital. Now this excludes scandium and zinc. They are in the D block, but the ion rule means that they are not transition elements. Transition elements form compounds with more than one oxidation state. Now, the number of oxidation states increases up to manganese, and then it decreases, but they all form +2. Different oxidation numbers have different colours, and we'll use this later on to identify them. Different oxidation states form different coloured compounds. For example, chromium-3 is green, whereas chromium-6 is orangey brown. These are caused by partially filled d orbitals of the metal ion. They make great catalysts, and you know this because iron is used in the Haber process, vanadium oxide is used in the contact process, and nickel is used in hydrogenation. And you can either have a heterogeneous or homogeneous catalyst. Heterogeneous meaning different state, homogeneous meaning same state. And now something you haven't come across before, ligands or ligands, I'm not entirely sure how to say it. Now, however you pronounce it, they donate a pair of electrons to a central metal ion for a dative or coordinate bond. The number of coordinate or dative bonds it forms is called its coordination number. And there's monodentate and bidentate ligands, one pair of electrons and two, hence mono and bi. Complex ions are when one or more molecules or anions are bonded to a central metal. To represent complex ions like this, the ligand is in brackets, the charge is on the outside of the square brackets, and the square brackets are there just to show you that you're grouping everything together. The number of coordinate bonds determines the shape of the molecules. 6 coordinate bonds makes it octahedral, which is an angle of 90 degrees. 4 coordinate can make it tetrahedral, which is 109.5, or square planar. Square planar will only work if there's 8d electrons, and this includes elements like platinum and the others I've listed here. Now, if it's octahedral, we're going to say something like hexaagua, 6 water, or if it's tetrahedral, tetrachloro, 4 chlorine. Now, complex ions can form stereoisomers, but it depends on the type. And it also depends on the number of ligands bonded to the center metal. 4 6 coordinate ions require 2 different monodentate ligands to form cis or trans isomers, whereas with just 6 coordinate ions, both ligands will show cis trans isomerism and also optical isomerism. So how does cis trans isomerism work if there's no C to C double bond? Well, it only happens in some square planar and octahedral complex ions. And square planar cis trans isomerism requires 2 identical ligands and is exactly like organic cis trans isomerism. If they're on opposite sides, they're trans. If they're on the same sides, they're cis. For monodentate octahedral, they look like this. If they're at 90 degrees to each other, they are cis. If they're at 180 degrees to each other, they are trans. Now, for bidentate complex ions, it is very much the same case. The chlorines in this are 90 degrees from each other, and so it is cis. Octahedral can also generate optical isomers or enantiomers, and you can see here that these two are mirror images of each other, and these can also occur in any complex ion containing 3 bidentate ligands. Now, the spec specifically mentions cisplatin, which looks like this. Now, it is a tumour-attacking drug, but it can lead to kidney damage. It forms a platinum complex inside a cell's DNA. This stops the cell replicating, and so brings about the cell death. As the name suggests, ligand substitution is when you replace at least one ligand with another. Now, the ligand substitution is how you get colour change. So, for example, in this one, you're replacing all the water with ammonia, and it's going from a pale blue to a dark blue complex ion. And so 4 H2O ligands have been replaced by 4 ammonia, and both complex ions are still octahedral. This is actually the test for copper, and when you do it, which we'll discuss later, you add the ammonia dropwise and it will show 2 different reactions. So it goes from transparent blue to like a deep sea blue, and then to a dark blue. So hydrochloric acid is a source of chlorine ions, and so it can be used in this substitution, where it changes from pale blue to yellow, and it goes from octahedral to tetrahedral. Now, there is no change in oxidation number here, but chloride is larger than H2O, and so they can fit less around the metal, and so hence the change in oxidation number. Now, when you take this hydrated complex ion and you dissolve it in water, you change it to a pale purple. Now, it's important to note this is different to this complex ion, which is pale green, and their H2O has been replaced by one SO4. When you react this complex ion with excess aqueous ammonia, it changes from violet to purple. Now, hemoglobin is mentioned specifically in the spec, and it transports blood in the body, and the prefix heme means the central group of Fe2+, and this allows it to bind to oxygen gas. Now, the lungs have an increased pressure, which allows your hemoglobin to bind to oxygen, which is then released into your cell, and the reverse is true for any carbon dioxide that it takes from your cells. Problem arises when it comes to carbon monoxide, because carbon monoxide can also bind to iron, and it creates something called carboxyhemoglobin, as opposed to oxyhemoglobin, which is just oxygen. And so this can cause danger because it limits your breathing and obviously all the other dangers that come with carbon monoxide poisoning. Now, a precipitation reaction is when two aqueous solutions containing ions react to form an insoluble solid. And with a transition element, if you add in sodium hydroxide and ammonia, you will form a precipitate, some of which will be able to dissolve to form complex ions. So I have written down here all of the reactions of the transition elements that you need to know with hydroxide ions and the colours that they form. Now, I've used solid instead of precipitate purely because I couldn't fit precipitate on the whiteboard, but hopefully you still understand what I mean. So copper is blue to blue, iron is green to green or orange in air, iron 3+ is pale yellow to orange, and then manganese is pale pink to a light kind of brown. Now, chromium is a special case. It's a violet solution to begin with, and then it turns kind of a grey-green precipitate, and then you add some more and it becomes a dark green complex ion. Now, you can dissolve precipitates in ammonia, so copper goes from pale blue to deep blue, chromium will go from green to purple, and iron 3 and manganese do not dissolve at all. Now, these are the tests for these metals. Now, you can oxidize iron into iron 2+ with the use of iodine, and you'll see it change from an orange to a pale green solution. You can use electrode potential to explain this, so there is a more positive electrode potential value, and so equilibrium is more likely to gain electrons, shift to the right, and so undergo reduction. Now, you can react dichromate ions with zinc to end up with chromium ions, and obviously the color changes orange to green. If you add an excess of zinc, you can reduce it further and it will go from green to pale blue. And you can use electrode potential values to explain this as well, because it has a more positive electrode potential value, equilibrium is more likely to gain electrons and shift to the right and undergo reduction. You can reduce copper 2 ions into copper 1 ions through the addition of iodide, and it will go from pale blue to a white precipitate. You can form pure copper by disproportionating copper oxide, which you can see here. You can see here that copper is both reduced and oxidized, and that's why it's disproportionation, and it forms a brown copper solid and then a blue copper sulfate solution. Now, the spec also specifically mentions knowing your test for anions, but they're all exactly the same as Module 3, except for the one for halides, where instead of silver nitrate, it asks you to react it with just silver ions. And it also wants you to know the test for ammonium, which again is in Module 3. And if you're in any doubt about any of these tests, definitely just go check out my Module 3 video, and I should have explanations there. It also asks for the test for transition metals. These are the reactions we did with aqueous sodium hydroxide earlier and the coloured precipitates that they form. So definitely just skip back, must be 3 minutes ago, and take a look at those. So that's it for Module 5, we've finally finished it. Next week we'll start Module 6, that'll be another 2-weeker because it's a massive module in the spec, and then after that we'll start doing past papers. So I really hope you enjoyed and you found it slightly helpful. Please remember to like and subscribe, and I'll see you later. Bye.